What color was the dress actually?
Oh, so now we're back to the color was the dress actually.
It's blue and black.
It was blue and black. Yeah, it actually was blue and black. But it sure is fun to try and figure that out. I enjoyed watching everybody argue over it.
I did send you an email that links the juniors to the like the regular lab rep level video.
Oh, okay. Yeah, they should have all the links we get there.
But then also at the same time, it also didn't show the slides, it only showed us.
Oh, okay. Weird.
So it was more like an audio lecture than.
That's bizarre. So it didn't show that?
No, it just showed the us. Well, not us, the juniors.
It's not supposed to be, because it's supposed to be screen recording. Screen share. Maybe that's the problem. You know what I bet it was? So I have a tutoring gig now on Wednesdays, and screen share is like kind of an automatic set in here, but I had to take it off for him, and I bet that's what happened. Thank you for telling me that. Xander, where'd you go? At me.
Yeah. And homie had like a plug, that's like pinkish purple, and I sent it to my group with Liam. Me and Liam said.
Oh, the shoe and the nail polish?
No, it's like,
Y'all sent that to me.
no, it was like a,
It was a little charging.
no, it was like just a little
Yeah.
charging thing, and like it was purplish pink, and I sent it to him and Liam, and both me and Liam think it's purple, Lucas thinks it's pink.
Oh gosh, it's one of those. How is it purple? How is it
You're
pink?
blind.
I love it. All right, Jordan, this is you. You. All right. Okay, let's roll. Yeah, in the past, I had to hit the screen share for everybody to see it, so I bet that's what it was. All right, light and optics. Did everyone have fun last week trying to guess what colors were what colors? That was entertaining. Or were you more frustrated? That's okay. Anybody who wears glasses or has ever had an eye exam will identify with a couple things in today's lesson too. All righty, so mirrors. So somebody tell me the law of reflection. All right, Yusuf, your hands up first. What up? Huh? Try again. Law of reflection. You weren't even ready for your hand up.
I got the angle, I got a ray diagram, but I don't got the law.
Does anybody have it? All right, law of reflection states that an angle of reflection is equal to the angle of incidence. So this is what we did in lab. Remember, you got your surface here, you got a perpendicular line here, right? And you have an angle coming in like that. That's your incident angle, and your angle of reflection is going to go the opposite, going to the opposite direction. But the distance, I mean, the angle between each of those rays and that imaginary perpendicular line there is always going to be the same. All right, and here's exactly what I just said. So, what's a ray diagram show, Caitlin?
Shows how the rays change direction and
There you go. Okay, so this is what we were doing in lab. If you have your mirror here, right, then you have this normal line, and that's this imaginary perpendicular line. If it's a perpendicular line, then what's the angle between the normal line and the plane mirror going to be? 90, spot on. Okay, so you have an incident ray that's going to come in. Here, sorry, it's up here. The incident ray is going to come in. It's going to hit your plane mirror, and it's going to bounce out. And if you have that normal line drawn perpendicular, the angle between the incident ray and the reflected ray is going to be the same, right? And that's what Caitlin was just saying. That's perfect. All right. So the angle of incidence is then which side of this, Xander?
The angle of the incident, it makes with a line being drawn perpendicular to the surface of the mirror.
Right. So this is, if we call this the normal line in the last image, right? So this is our little perpendicular line that's imaginary. and your angle of incidence is between the incident ray and that line. So then the angle of reflection is what? Jordan? Was that a hand or not a hand? I'm not sure. Was that your hand? Oh, you're swallowing. Good. Swallow first. Please don't choke. Yeah.
The angle of reflection is the angle that the reflected ray takes out of the system.
Right. Between this imaginary normal line and the reflected ray. So this is your angle of incidence, this one here. This is your angle of reflection. If you were to add your angle of incidence and this little bit here, what would you get? What number would you get?
She gets 45.
No, 47.90.
If you add this to this,
Oh, they should get 90.
you get 90. Yes, right.
I think that you were talking about just the incident rate to the.
Ah, yeah. And if you get, well, yeah, if you add this to this, yeah. Now, in this case, so if you were to, what if you were to add all 1, 2, 3, 4 angles? What? Go ahead. Yeah, 180. Just making sure you're all paying attention. So yes, there's your angle of reflection, like Jordan said. All right. So this gets a little wonky. So you got to kind of follow along here. Yes, ma'am.
He's trying to join the live stream.
Okay, let me see. Thank you for telling me that. Look, hold up. Let me see. Oh, come on. Get bigger. Oh, don't do this to me. Hold on a second. It's going to be dumb. Where is he?
I don't think he's even joined yet. He was telling me that he doesn't have a password.
Oh, it's Rico 2324. It should be 2425, but no, 2324. I got it right. I know what year it is. I know what year it is.
2425 steps here.
I'll hold on a second while I'll come back to it. So yeah, let's go right back here for a minute. So while we're giving him a second to pop in, I don't want to invite him yet. He can pop in on his own. Doo-doo-doo. Come on, James. Maybe not. All right, so for a minute, while we're waiting for James to show up over here, y'all keep in mind that for a minute, you're gonna kind of have to sort of forget some of your familiar vocabulary, because this stuff gets a little weird. We call this, trying to wait for him to show up. We have real images and virtual images, and the words aren't quite what you're gonna remember them to be. So, is he coming? Do you know? Is he trying to pop in?
Said no.
I don't know what that means, but
Nico, updates lowercase.
anybody know his email by heart? I can look it up. Does anybody know it?
Know what?
His email by heart?
Oh. No.
I haven't seen your brother.
Yeah, should you know it? Huh?
James Dolly 07.
Okay.
Oh.
Ah. Let's see if we can invite him. Yeah, why would I know that? She's like, hello.
Emailing my brother.
Let me try it. Okay, wait a minute. Hold up.
It's good that we started early then.
Yeah. Yo. There we go. Come on. Oh, geez. There he is.
Beautiful Google profile picture. Cameron Princess.
All right, I sent it to him, so hopefully he'll get that now. All right, back to where we are. All right, so for a minute, you kind of have to imagine here that you're dealing with language that's not what you think it is. So real images are those that can be projected onto a screen. And if you think about an old school projector, like the kind in movie theaters that the light shines through the film and the film goes by and it actually makes an image, these are real images, okay? But then, and they're often upside down, so sometimes they're actually, the projector is upside down so that the image is right side up, right? And then you've got, come on, James. There, hey, James. Everybody be really loud and say, hi, James. No, it says he's in. Go ahead. Say hello to him. We're all been waiting on him. Everybody like, hello, James. We're all waiting on you. There we go. Okay. Yeah. Okay. Now back to where we were. There we go. All right. So they can be projected onto screen. They're upside down. They're smaller than the actual object, and they can be formed by convex lenses or mirrors. Now, virtual images cannot be projected. Huh. They're right side up. They can be bigger or smaller than the actual object, and they can be formed by concave lens or mirror or a convex lens or mirror. So how's a convex lens or mirror going to be on both sides? How can it be real and virtual? So in a minute, I'll show you a video that shows exactly how it can be real and virtual. And once you see it, it makes perfect sense. You're like, oh, yeah, okay. So what is a plane mirror, Miss Chloe? Yeah, a flat mirror. Probably the kind you look at yourself in unless you really like to go to the fun house, because that's kind of, yeah. Those fun house mirrors, you know the ones I'm talking about, right? The ones that are all curvy. Yeah, those are fun. Those are not, well, those are plane mirrors, but they're plane mirrors that have convex and concave portions, right? Right.
Why is the rat in the muse so much bigger than the other rat?
It's a demon.
Perspective.
Oh, wait, we got one coming up where the rat has an extra leg and I didn't catch it till this morning. It's fun. All right, so what type of image is produced in a plane mirror? Who was going to say? Bailey, were you going to say? Yes, this is a virtual image. Okay, so basically what this means is when you look in a mirror and you see yourself, you can see the image, but that's not really there. That's the light bouncing back at you. Like if you touch the mirror, it's not a projected image, right? It's light bouncing back. Uh-huh.
Can you tell me what's happening in that picture?
He's looking in the mirror. The more time we spend doing that though, the less time we spend on actual lesson. Like, yeah, it's a picture of a rat looking in a mirror. No, that's fine. It's neat. It's artsy. It's artistic.
The 3D mirror.
All right, concave and convex. Okay, Chloe, what's a concave mirror? Which way does it curve? How would you describe it? Don't wave. Don't wave. Yeah, in like a bowl. That's right. Yeah, in like a bowl. So the curved surface is on that the curve is inside, not outside. Okay. So what do you call the point which all the light rays meet, Liam? Right, there's your focal point. Okay, and then what do you call the copy of an object that's formed at the focal point, Caitlin?
Real image.
Okay, there we go. So look at here. What kind of a mirror do we have? It's concave because it's like a spoon, right? All right, now, what type of image did we say a concave mirror could produce? Drew?
Upside down.
Upside down?
Upside down.
Ah, we'll see, right? You're right.
Real.
Real and virtual. That's right. Okay. So you're right. It can be upside down. Okay. So we're going to see it in a minute. I'm going to show you how it does both. So what kind of mirror are we looking at here? This is yeah. Go ahead, Bailey. Yeah. This is convex.
Yeah.
Right. Okay. So look, in this case, it's just a chrome bumper, but you can see how that chrome bumper could serve as a convex mirror, right? So, yep. So how would you describe a convex mirror, Yusuf?
Mirror that curved inward.
Not inward, but
Outward.
outward. Right. Okay. So the reflecting surface is on the outside. So your convex mirror is like this. Your reflecting surface is on the outside. Your concave mirror is like this. The reflecting surface is on the inside.
Concave is a cave.
Yep, I was about to say, how do you remember? Concave is like a cave that goes in, right? Goes in as opposed to the other way. All right.
Convex is nowhere to go.
So what type of images do we get with convex mirrors, Caitlin?
Virtual because they spread the light.
Yeah, okay, exactly, because they're spreading the light. I want you to get a good look at that guy. See how he's a little distorted there? Okay, you may see who has been driving or even riding and seen a convex. Yeah, where did they put him?
They put them at really sharp turns, or when people are backing out,
Mm-hmm,
that they have mirrors. I've also seen them at the park,
mm-hmm,
like on the trails.
mm-hmm,
They have them so that it's when there's like a blind turn, like a really blind curve.
mm-hmm.
People riding bikes or those cars can see because of like the trees.
Yes, you
Everyone
can
can see
see, because they give you like, what were you gonna say?
School buses have them in addition to the regular side mirrors.
Yes, they do, up in the front. Yep, they're the real big ones are on the front of the school bus, right? and they give kind of a panoramic view because they kind of scatter, right? So you may see them at certain intersections, and that's the purpose. There's one particular wedding venue that I used to work a lot. I haven't worked it in a while, but I used to work it a lot, bring cakes up there, and they have like a 1 mile gravel track, single track dirt road before you get to the property, and it winds through the woods. And then there's like a 90-degree turn at one point, and there's a giant convex mirror on a tree, and you can see if somebody's coming, because otherwise you're stuck. I mean, you can't see around. It's totally a blind curve.
We used to go on that trail actually, and then one time this big bus just came out and we almost hit.
You're hanging out at Neverland Farms? Probably a similar one. Yeah.
Oh.
This is a particular wedding venue. Yeah, you gotta be special to get on there. Like you gotta be bringing something or getting married or watching somebody get married, because it's a big place. All right. So you're going to see exactly what is meant by concave mirrors producing real and virtual images here. And remember about real images being upside down? Remember? So you'll see exactly what that means here.
My friendly little bulldog, and we're gonna show what
I
happens.
think this guy's from Georgia.
Notice right now it is enlarged.
But the
and
dog.
Inverted. As I move it towards the focal point, enlarged, and it will be at the maximum size at the focal point. Now, as you move towards the center of curvature, look what happens to the image. It will begin to get smaller, and it will also be inverted. Okay? So there's Mr. Bulldog, inverted and smaller, and as you go further away, it's going to be smaller. Now let's see this in reverse. It is inverted. At the focal point, you will notice that the image is at its maximum. It is enlarged. Okay? And then beyond the focal point, getting closer, it now is no longer inverted, and Mr. Bulldog sees a large image of himself. I think that's pretty cool. Concave mirror, it's because of the way the focal point. Okay, let's take a look at an image in a convex mirror. They're able to show panoramic views because of the way light is reflected and the focal point. Notice the headrest on the seat, and now let's compare that to a regular camera. I'm in my van and I happen to have two types of mirror. And here's the image in a regular van.
So that's the regular plane mirror.
Headrest. You're only seeing the headrest on the left. And now let's go back to the convex. And you will notice that you can see the headrest on the left plus the other seats, a panoramic view. Convex. Regular mirror. Kind of cool.
Anybody have one of those mirrors in your car? Yeah, I was gonna say, you can do it with the spoon. If you're, go on, move. Yeah, if your vision is good enough that you can get the spoon to a place where you can still see your reflection, you can watch it flip. Are you watching yours in the spoon over there?
Like right up, let me see it right side up.
Like it's right side up, it's that close to your eyeball, right? It's real close. Where does it flip?
Flips like right there.
To about 3.5 inches from your eyes where that spoon flips. So you can do that. You can play that fun game with yourself. You're bored. Yeah. All right. Lenses. Who here is good buddies with your optometrist, or at least goes once a year? Yeah. Okay. Here we go. All right. There you are. So what causes light to refract? All right. Anybody want to give me some, Milo, what you got for this? That's right. Okay, so light's going to enter a different medium, and when it hits, it's going to change the speed at which that wave of light is traveling, and that's what causes it to bend. This is like we talked about, like if you put a straw in a glass of water and you're looking at it from the outside, the medium is just air, but once you're inside the glass, you have the glass and then the water that the light's passing through, and it's slowing down, and that's why your straw looks bent, right?
Might even fit, it looks like not attached.
Yeah, sometimes it looks completely unattached. That's right. So anybody got a definition of lens for me? BJ.
An object made of a transparent material that has one or two curved surfaces.
Yep, okay. So an object made of transparent material that has one or two curved surfaces. That's perfect. This guy has discovered some cheese. He's very excited about his discovery. Look at that. The mystery of the stolen cheese. He has found the cheese. You know, that's particularly funny. You know what I asked AI to do was give me an image of a rat using a magnifying glass, and AI put the cheese in. I didn't ask for the cheese. That's pretty good. That's pretty good, GPT. All right. So concave and convex lenses. So we talked about a concave mirror. So a concave lens is the same idea, right? It's curved inward at the center and it's thicker at the outer edges. And what types of images, Yusuf?
Only virtual.
Okay, only virtual images. All right, all right, all right. So then we have convex lenses, and it's the same thing we said for mirrors. It's curved outward, and then they're going to produce what?
Either virtual or.
Virtual or real. Okay. So we had the concave mirror that produced what kind?
Concave is virtual and real.
Right. And then with lenses, it's the other way around, right? There's your convex doing virtual and real. So they're kind of flip-flopped. You can keep that in your head. So what's critical angle? Anybody know what that is? You want to do it, Jordan?
It's the angle where the index,
Mm-hmm.
it's the angle where the ray of light
Mhm.
will slow
Don't wait.
down and then go at a 90-degree angle.
There you go. Okay. All right. So basically what you got is the critical angle is the angle of incidence. So that's the light coming in, right? That produces an angle of reflection of 90 degrees, which is what a lot of you were seeing today, like with your the little curved mirror in particular, right? So then what's total internal reflection, Lucas?
Coming out of the hose.
Fiber. What's the answer to that question I just asked? Your hand was up. Yusuf.
Complete reflection of the light.
There you go.
Going back to its original medium.
Okay, yeah. So the reason I picked this complete reflection of light ray back into its original medium. Okay, so the reason I picked this image or made this image is because there's fiber here. Okay, fiber optics we're going to talk about. If you like coming to class here, you have fiber optics to thank because that's what Jason does. He works in telecom with fiber. Like that's his whole life is fiber. So this right here is going to show you exactly what total internal reflection looks like. And you need this type of thing if you're going to work with fiber. Okay, so watch him turn this light beam. See it bending? So that's the refraction in action, right? Do you see what's about to happen? Watch, look. There you go. Everybody, whoa, what?
What's the left?
Happening? Kind of cool to watch that, right? Like that's just really neat, right? So he's showing there's a diagram of it. And I really love that this guy is a true scientist because if you look right here, do you see what he has written? Angles are accurate to about plus or minus 1 degree. I'm giving you my scale and I'm telling you how accurate it is. All right, so you saw that happen. All right, now watch here.
Total internal reflection is important in technology a lot of communications are done, including telephone and other communications. You may have an optical cable in your home stereo or home theater system that communicates information through an optical cable. The principle is total internal reflection. If we come in at a glancing angle, then all of the light that's incident on this surface and on this surface will be reflected back internally into the
That's
material.
cool. I could do that all day.
So-
It's fun.
So it works for glancing angles, and the beam needs to be confined within a material that is more optically dense, has a higher index of refraction than the surrounding material. But any shape will do. You can use a rectangular shape here, you can use a circular shape. Confining all that light fiber. Now, this is a more typical light optical cable or light fiber. I'm just going to introduce the beam here. You'll see it come out on the far end. This is an example of, we have a source of light in the base here. And each of these, all they are strands of plastic. They are channeling the light through them. And they can be bent or whatever, and they'll still channel that light. There is a certain radius, if you bend it, if you kink it really hard, then that brings you away from the total internal reflection, and you lose the effect. But very effective, very important in today's technology, total internal reflection.
You ever seen those lamps?
Yeah.
So when I was a kid, that was what you got, like that was the thing I wanted at the circus. When you went to the circus, they had these little like cheap plastic flashlight type jobby doos with those fibers on top. And they had like a little turning light inside. They changed color. It was like the coolest thing ever when I got them. The whole crowd had had them. You'd see all these little lights everywhere. But that's every year we went to circus every year when I was little. And because it always came around my birthday, so it was convenient. But I wanted one of those every year. They were fun. So if you have any kind of fiber optics that go to your house or are in your house, that's how they're working. So interestingly, they can shoot that light a pretty long way through it's glass fiber. That's what's outside and buried and in the house and whatever. And they can shoot it a long way, but they do get to a point where they have to amplify it. And they have little amplifying stations along the way. And so those entire networks, that's what he sells, are the networks and then the services that keep them running. But it's really interesting. So this guy shows you how it carries data. Okay, that's the particular part.
If you've ever built a
It's
tree
fast.
fort, you've probably also tried to send a secret message to your friend using Morse code and a flashlight. And fundamentally, fiber optic networking works in the same way, encoding data in pulses of light that travel around the world, carrying our phone calls, business conferences, and important internet data. But now hold on a second. How exactly do you send light over great distances and still manage to extract information from it? I mean, fiber optic cables have to carry light for literally thousands of miles, like across oceans. Yet, if you've ever shined a flashlight down a long hallway, you'll know that over any more than a short distance, the light scatters and eventually becomes too dim to make out. Well, that is where optical fibers come in. Those really skinny tubes that make your Christmas tree look nice without having to string up any messy lights have some special characteristics that allow them to work over incredible distances. The main way that fiber optics behave differently than your flashlight is that they take advantage of a physical phenomenon called total internal reflection. You see, a fiber optic system doesn't just shine light down any random hollow tube. Instead, optical cables are made up of a core of glass or plastic surrounded by an outer layer called cladding. Both the glass and the cladding have an inherent property called a refractive index, which is basically a measure of how fast light can travel through something. For the system to work properly, the cladding needs to have a slightly lower index of refraction than the core. Now, sometimes this is achieved by using pure glass, that is silicon dioxide, for the core, and then doping the cladding with chemicals to lower its refractive index, while other times the core itself can be doped to raise the same value. Either way, this difference means that if light hits the cladding at a shallow enough angle, it will be completely reflected at the same angle instead of passing through the cladding. That means that it can continue on down the fiber in a zigzag pattern indefinitely, or well, not quite. Although in theory, the optical signal shouldn't just keep going all the way until it reaches the other end of the fiber, the pesky real world always has a way of throwing a wrench in the pudding. No matter how high-end and pure an optical cable is, there will always be some imperfections, even if they're so small that you could only see them at the molecular level. And these will cause some of that light to scatter, weakening the signal over distance until eventually it can't be understood by the equipment at the other end. So to combat this, long-distance fiber runs are assisted by repeaters or amplifiers. A repeater gets placed at a point down the fiber where the signal will have weakened significantly, but it's still strong enough to be read. Once the light hits the repeater, it's turned into the corresponding electronic signal, which is then turned back into light, much as it was at the origination point, and then sent along on its merry way. Repeaters come with a latency and a complexity cost, though, so many modern long-distance systems now use amplifiers instead. These gadgets have optical fibers which are doped with chemicals that directly amplify light when the weakened signal hits them. So the ions in the fibers themselves will re-emit the same signal, but much more strongly than what came in, and it continues down the cable. In this way, optical fiber runs can be designed to be really long, making them a more viable choice for long-distance communication than copper. Optical fiber is not only more cost-effective than copper wiring, it's more power efficient, and it even goes farther without requiring a boost. Also, because it's thinner and doesn't cause electromagnetic interference to the cables around it, it's common to bundle a bunch of optical fibers, each of which can carry multiple wavelengths of light into one large cable, making it possible to transmit enormous amounts of data without taking up too much space. This versatility means that fiber optics have found uses outside of just communication, such as in endoscopy, where their flexibility allows a user to light up and view inside very hard to reach spaces. This is useful in fields like engineering, plumbing, and even medicine. Speaking of which, I gotta run and get to a doctor's appointment that hopefully doesn't involve sticking a fiber optic scope up somewhere embarrassing. Oh, I know what the doctor ordered. This message from our sponsor. Getting great at math, science, and computer science doesn't have to be dull. Really, it's a problem-solving website
You gotta love
and app with a hands-on approach with over 50 interactive courses.
He does have some
Brilliance
video.
courses have
Yeah.
storytelling, code writing, interactive challenges,
Da-da-da.
and problems to solve.
Dee-dee-dee-dee.
And with Brilliant, you get to unravel concepts.
Yeah, there you go. So here's a question. So if you're out and about and they're doing construction on the side of the road, sometimes you see little flags, little colored flags in the ground. What are they there for?
To mark different things.
Yeah, what kind of stuff are they marking?
Gas lines, water lines,
Mhm.
lift lines.
What
water
color are the ones that mark the water
I
lines?
think those are blue.
Those are blue. What color are the ones that mark buried electrical cable? Red. What color are the ones that mark natural gas lines?
Red.
Yellow.
Yellow. And how about fiber? Orange. When you see the orange, that's the fiber. I don't know this stuff. I get told this stuff. We'll be driving along. It's like, you see that on the pole? You see? Actually, there's those big boxes. They're transformers and they're also communication boxes and whatnot. Like there's one at the back entrance of the neighborhood, and he was riding his bike past it the other day, and it was open, which means that whoever is team to check it didn't lock it because they have a special key. So he's all calling, calling the utility company to tell them their box is open. And that's not good. You could real easily mess up something. I will tell you this, communication wise, this is interesting. So all these fibers and things, they run these massive networks. Most are redundant. There are like multiple loops. So if one goes down, there's another functioning, that kind of thing. And it'll go from like, it's like your grounded data, like what's in your house that people plug into, but it's also can affect phones. Like their gear had a failure last week, and it was like T-Mobile was gone for like 2 states, that kind of thing. So it's a big problem when something fails. So there's always redundancy. And it's always a challenge, I know, in that industry to get the customer to keep buying new equipment because it's expensive. It's multi-million-dollar every time they build out any kind of network. Millions and millions and millions. Like the little boxes, those amplifiers are like several $100,000s a piece per box. And there's a lot of those. So there's a lot of that going on. But all of this stuff feeds into these centers, these buildings, and they're everywhere. There's one in Atlanta. So when you're ever in a city, in a big city, and you see a building that's like a big, tall, boxy, ugly building with almost no windows, it's almost always a telecom center. And it's interesting because like there's one in New York. Do you remember the address? Daddy talks about it all the time. It's huge. And we walked past it once and he's like, there it is. But this one, always thinking about work, is like, I don't understand why that hasn't been a target yet. Like a big target, because if you take out one of those, you take out a lot. Like that's a big thing. So those are everywhere, and you'll see them, and you don't even notice them unless you're looking for them. And then when you do notice them, it's like, whew. And all this stuff they run through conduit, right? They actually have, I think it's called a mouse or a rat or something, but they can fire the cable down the conduit. And it can go a long distance. So that's how because they'll bury the conduit and then they'll fire the cable down and it just shoots all the way down the conduit, which is really kind of cool. But do you remember when the interstate caught fire about 5 or 6 years ago? Anybody remember that?
Yeah.
Yeah. 85, right almost where it hits the top of the connector. Oh, no. The whole interstate, there were memes about like the Dukes of Hazzard generally jumping off the hole in the interstate because there was a giant hole basically. But it was because there was fiber conduit, which is all rolled up on a big roll, right? A big reel of stuff. And it was under the interstate, and there was like a homeless encampment there. And there was fires to keep people warm, and somebody's fire got near the conduit, and the conduit's like petroleum based, right? It's like a plastic. So, yeah, fun times. So what types of materials is total internal reflection likely to occur? Caitlin.
Materials that have small critical angles.
Right. So it's materials that have small critical angles that are likely to cause most of the lights entering them to be totally internally reflected, which tends to be those transparent materials like he was talking about, particular types of glass, very pure glass that they've quote unquote doped, right? You add stuff to it. All right. Telescopes. So somebody define a telescope. Yusuf.
An instrument that uses a lens and mirrors to cut and focus light from the scene.
All right. And there are 2 main types, and they are what? Liam.
Reflecting and refracting.
Yep, reflecting and refracting. Reflecting and refracting. See, now you made me get I'm blaming you. So reflecting has what in it? Lenses and yes, lenses and mirrors. And then refracting has just PJ, just lenses, right? Okay. Telescopes and microscopes are pretty much the same technology applied differently. Okay. Cameras. All right. Pinhole cameras, modern film cameras, digital cameras. What's a camera? Lucas.
It's something that looks the image of an object.
Okay. So when we're talking about cameras here, how does this camera form an image from light? What do we say? What did anybody write? Anybody have anything? No? Okay, so what it does is your light rays are going to come into the camera through a little opening called an aperture. Anybody ever seen the Falcons, the Mercedes-Benz Stadium? See how the roof functions?
Like a camera shutter.
It's exactly like a camera shutter. Yep, it's got like these turning pieces that fit together. That's an aperture on a camera. The light comes in and then it forms an image on film. Okay, this is not your phone. This is an actual film camera. So back in the ancient days, right, we used to have to buy a roll of film. A good roll of film was the one with 35 pictures on it. Before that, it was 12, 24, 35 was awesome. You got 35, right? And you pop a little 35 millimeter film into your little camera and you went to your party. Okay, you go today, You're taking your camera and your phone and you're snapping pictures, and if something looks bad, you're just deleting it and moving on. Or your light's bad and you're raising the light and changing the warmth and the tint and the shadows, right? You can do all that. We would take this camera, he's like, I'm doing it. We would take these cameras to the parties, wherever, and we'd snap our pictures. And then you had to take the film out and take it to like CVS or Costco or a photomat. If you ever see these random, like older shopping centers, and there's like a weird little box in the middle, it's usually a coffee shop, that used to be a photomat. You dropped your film off there and then you came back 2 days later and picked it up. And then they printed out on paper, and half of them were crap, and you ditched them because they were blurry, there was no light, there were shadows, it was terrible, terrible. You went through 35, you might get 24 you get to keep because the rest were terrible. We've gotten so much better. It's great.
How much megabytes or gigabytes is the 34 pictures?
There's nothing. It's not digital. It's not digital. Paper. The film is actual film. Your parents probably still have some film at home.
Yep.
That's been exposed. It's been film that's been exposed. So it's the negative basically. So it's a whole process. Like they had to dip them in chemicals or that was if you had like big photos, like you were a photographer. Otherwise they ran it through a machine. Yeah.
I remember my mom talking about like certain films can like blend in together.
Yes, you can get a double negative.
Yeah.
Oh, it's so weird. You get like this superimposed head from somebody else. And you're like, oh, what happened there? Or you can expose it twice. Like you take a roll of film that you thought was new and it wasn't, and you put it in the camera and then you took pictures on it. And then what you get back are like these superimposed pictures on pictures. And it's really weird because they'll be like, your friend with her birthday cake. And then behind her is like a Halloween picture of like a guy dressed as Frankenstein, and he's kind of behind her, kind of in front of her. It's very weird. Like these are the same process. This is the same process. That's a negative. This is a slide. And it's actually like, this is Neanderthal man, ancient men, whatever. This is an antique one. But you would project light through that and kind of see it if I put it up there. Right. But this you would project and make a real image elsewhere with it. But yeah, but the actual film, like X-ray film, you ever see when they do your teeth? Or does everybody go to a place now where it's on a screen? Screens are, yeah, in the last 10 years or whatever, it's been almost all screen. Yeah.
I was used to be on the
Yeah.
I
I have one over here somewhere. I have a tooth. Oh, there it is. That's an X-ray film. These are teeth. These are somebody's bottom teeth. You can see them, right? Same thing. Oh, James's teeth. Ah. So yes, anyway. All right. So cameras. This shows you just how far we've come. Be thankful for that one on your phone, man. I take more pictures now than I ever did. So much easier.
Kids, I'm going to tell you an incredible story. The story of how I met cameras. Would you believe me if I told you that the first camera to take a permanent photograph was invented 100 years before the camera was available to the middle class to document daily lives? Reportedly in 1685, Johann Zahn, a German, proposed a design for what is now known as a handheld reflex camera. However, nobody physically realized the camera until 1816, when Joseph Nicephore Nips constructed a prototype. But his first images were not permanent because Nips' camera was so simple and used paper coated with silver chloride, which would produce a negative image. Because it should have been light, but it was dark. Silver chloride works when exposed to light, but Nips couldn't know that. Nicephore Nips may have created the first photograph in 1816, but his experiments with camera obscura, an ancient technique for capturing an image using a small hole in the wall of a dark room or box, had been occurring for years. The camera obscura technique was used by many painters in the 16th century to produce some of their works. For example, Caravaggio used the technique in many of his paintings.
There are artists that still do this.
After Niepce,
Not a dead art.
his collaborator, Louis Daguerre, continued his obsessive work on creating a permanent set of images. In his work using silver material, he succeeded in making the camera that we call daguerreotypes in 1839. Daguerreotypes produced positive images, unlike the negatives of Niepce. Henry Fox Talbot's calotype, a daguerreotype variant, was also popular. The daguerreotype would be replaced in 1850 by a new wet collodion process, which required treating the plates before using them. This process produced sharper images and required a shorter exposure time. However, the next significant advancement in camera technology came in the creation of film. American entrepreneur George Eastman created the first camera that used a single roll of paper and then celluloid film called the Kodak in 1888. The Kodak camera could capture negative pictures, but they were sharp like daguerreotypes. At the time, Kodak said, "You press the button, we do the rest." Thanks to the popularity of Kodak products and the introduction of other portable cameras, film cameras made using image plate processes
Kodak still in
obsolete.
business.
Between 1905 and
Eastman Kodak
1988,
still in, yeah, still functioning.
introduced standalone rolls of 35 millimeter film
There it is.
to be inserted into and removed from the
Yep.
user's own camera. However, 35 millimeter or 135 film was introduced by the Kodak Camera Company in 1934 and quickly became the standard. Although Kodak has always planned to be a pioneer in camera production as a brand and develops many kinds of products, others have joined the race. In 1999, Nikon released the first professional DSLR that we know today. And in 2004, mirrorless cameras appeared without the need for a mirror, thus reducing the size of the cameras. But actually, the first digital camera was invented in 1975 by an Eastman Kodak American engineer, Steve Sasson.
Good thing.
Although Kodak elected not to commercialize Sasson's prototype, the digital camera was the future. While there's been more speculation on the history of the camera than any other inventions, we can see that who inspired whom was more important than who made which first. While most of us today have digital cameras in our pockets, high-quality DSLRs still have a role to play. The history of the camera is long, with many great leaps forward, followed by years of perfecting the technology. Today, we owe a debt of gratitude to these people who have enabled us to preserve our memories, not only in our memory, but also in a way that we can see with our eyes. Curious about the next story? Then turn on notification.
So, interestingly, daguerreotypes, sometimes they're, like, you ever heard tintype? As far as I know, daguerreotypes and tintypes are very similar. Sometimes people will call somebody like a tintype of their parent. Like this little girl's a tintype of her mother. It means like pretty much a copy, like identical. A lot of the daguerreotype, that era, there's pictures are on metal, like they're on a piece of metal. They're not on paper. And then you get to paper, like this is not anyone I know. My sister got me a box of Weird Oddities and this little baby came with it. But if you're looking, if you go to an antique store, or you can search online, but it's kind of interesting to do at an antique store. If you like weirdness, you know what I'm about to say, don't you? Okay, if you like weird things, slightly dark things, I'll let you in on a little, not so much a secret, but fact. So remember how they said that cameras were not initially available to the general public, right? They were very expensive. So to have a family photo taken was a big deal and very pricey. So wealthy folks would occasionally get family photos taken, but your everyday folk, if you're going to get a photo taken, you needed to have everybody there because it may be the only chance you ever get to get a picture of somebody. So do you know when they did that? You know? Somebody died. Yeah. So they would have a funeral.
Because there's dead people in some photos and you can tell.
There are tons of them. Do you know what they're called? So they're post-mortem photos. And there are thousands of turn-of-the-century photos that have families in them. And they're all, you had to freeze because it's not like snap. It was a long exposure. You had to be still for a long time. So a lot of those are blurry. Like this baby's eyes are a little blurry because it was probably looking around the room. So that they're not straight. Everybody had to be still. And you're standing with like your dead Uncle Jack. You know, you're there, you're posed, right? With whomever, auntie, whatever. But some of them are real weird because the only photos you got of people were when they died. So a lot of them were children, like infant death, because that was pretty common turn of the century. But they did weird stuff. Like there's one that you can find on the internet where it's like the mother is under a blanket and she's holding the baby, but it's like her arms are under the blanket. She's like a blanket ghost. and she's holding the baby. It's really weird. And it's like, And then there were people, and this was their whole career, to be specifically a postmortem photographer. And they had these entire apparatus constructed for posing dead people, like heavy weighted stands with like racks that came up, and you could put their arms and legs in so that they were standing like that. I'm serious. Like you've got a dead person standing up and posed, and they've got, and if they can't hold themselves up, and it's some of them are very hard. You can't even tell. Like you got to really, really know what you're looking for to know if you're looking at like a Victorian postmortem or just some Victorian dude smiling and looking fancy. But if you know there are certain things you can look for, there are certain clues that can clue you in. So if you're ever in an antique store and you start rummaging through a box of really old black and white photos, be forewarned, maybe not everybody in those photos was alive when you're looking through. So some of them it's very obvious and it's like, oh, and others you kind of got to wonder what you're looking at. So weird human history where we weren't quite sure what we should be doing with technology, and we don't do that much anymore, but we still do it sometimes. So yeah, we do. I mean, I've seen some interesting things. I saw a guy on a motorcycle once online. Like they posed him. That was it. There he was, sitting on the motorcycle. Guess that's how he wanted to go. Why not? All right. So what's a microscope? Who wants to go there? Okay, Caitlin, give me this one. Yep, a very small near object. So very much like a telescope, except you're looking at very small near objects. And what type of lenses does a compound microscope use, Liam?
The two convex.
Yep, convex lenses. Now you've got these guys down here, and then you've got the ones at the top, right? The ones at the bottom, these are the objective lenses, and then the one up by your eye is your eyepiece. So when we use our microscopes have this little turn dealio at the bottom, right? You turn it and you can pick your objective lens. So you have to multiply like the objective lens times the eyepiece. Like the eyepiece is usually 10 or whatever. And then you get different ones down there for the bottom to know your actual power. Okay, eye and vision. All right. Main parts of the eye are going to be your cornea, pupil, iris, lens, and your retina. So let's have a looky look. All right. So what is the inner surface of your eye called? Oh, Jordan. E. This part back here. Retina. Good. All right. I want you to look. Notice right here at the back of the retina. You see this fovea centralis right there? That's actually that's your focal point. That's where your beams of light are supposed to be focused, specifically on your retina. There is a condition called macular degeneration. That area is called the macula around the fovea. And see right here, macula lutea. So there are lots of capillaries there. And there are a couple different ways this can happen, but the more common one is called wet macular degeneration. Sometimes you'll hear it as AMD because it's age-related macular degeneration. So it doesn't usually happen to younger people. But all those capillaries can burst and bleed. And when they do, it causes like scarring and everything in that area. But it also, your eye is filled with liquid. It's called aqueous humor. And all that blood actually gets into your eye too. And so like this happened to my grandfather. He went to bed and woke up and could no longer see. And it causes all your central vision to go. So you have this kind of hazy peripheral, but your central vision is gone entirely. So we'd have to turn a little bit to even see you at all, not well. And his was so bad when it happened overnight, you could look like, and you could get him in the light and look into his pupil. And if the light was right, you could see the blood like moving in his eye. It was gross. But yeah, that can happen. And it is weirdly hereditary. So I'm like, yeah, please don't do that because that's gross. Terrible, right? Right? So, okay, let's see. C is the opening in your eye. PJ. That's your pupil. What color is your pupil? Why is it black?
Because it absorbs all the light.
Mm-hmm. Yeah. What else are we gonna add? Anything else to it or no?
It doesn't.
Yeah, it's like if you look through a keyhole into a closet that has no windows, just a closet, it's gonna be black inside, right? That's your eyeball. Your eyeball is like a closet that's black inside, and you're looking through the keyhole, and that's your pupil. That's the only place light's coming in. So if you were to get inside that closet and you had a little beam of light coming through your keyhole, that's exactly how your pupil functions. Okay, so then what's the colored part of your eye, Yusuf? Iris, right? That's the colored part. Now, your iris, if you look at it up close, it has all these like little filamenty looking things. It's like all these little stretchy. That's because there's a lot of little muscles and things that will contract and expand around your pupil. That's how you get like bigger and smaller pupil. You know, the doctor passes the light in front of your eye, trying to make sure your pupils are reactive. Like if you have a concussion, they might not be, right? People's pupils tend to blow up really big and they don't react when they have concussions. So that's fixed and dilated is what they'll say, meaning they're not moving, right? They're fixed. There's a weird condition called, I think it's anisocoria, and it can cause random dilation of one pupil and not the other. And there's certain things, sometimes people just live with it. Sometimes people get it with certain things. I get it. And it's weird as heck. The first time I saw it, freaked me out. Antihistamines and stuff will do it to me, and sometimes other things. But I'll look in the mirror and I got one pupil like this and one like this. And I have to put it like on my medical record, because if I'm in an accident and they're looking at me and I happen to have that going on, like maybe my brain's not injured, maybe I'm just weird, you know, because I am just weird. So that can happen and it's weird.
Does the color of your iris matter at all? Or?
It does for certain things. So that was my next thing I was going to say. So if everybody should wear sunglasses and protect yourself from the light, right? Because the UV obviously can be damaging and it can damage your eyes. And if you have a history of like family eye problems, like I do with macular degeneration, I am putting sunglasses on. But the lighter your eyes, the more uncomfortable you are in bright light. If you have darker eyes, you got nice dark eyes. Like I know you have nice dark eyes. You guys have darker eyes. Some of you guys have nice dark eyes. And some of us have like, mine are really light.
Mine are like the gray actually.
Yeah, mine are like super, super light blue. And if I go outside, like yesterday, I got out of the van and walked down to the mailbox to get the mail, and I had to stop looking at the driveway because the driveway was too light. I had to look at the grass.
That happens, like,
It's so stupid.
that actually happens with me.
Yeah, because your eyes are lighter too. The lighter they are, the more uncomfortable it is, and the more important it is for you to wear sunglasses.
Like if I'm on my, like, when I'm practicing at my ice rink, I'll like have to actually look up at the ceiling to stop my eyes from hurting.
Right, exactly. Yeah, because that white floor, that would make me crazy. Yep. So be aware of that. It absolutely does matter. And if you notice, like there are certain parts of the world where darker eyes and lighter eyes tend to be. And interestingly, like there's that whole chunk of like the Scandinavian countries, they tend to be very light eyes. They also are people who have lots of days that are just dark. And in those days that are dark, they need to absorb as much light as they possibly can. And that helps, right? Interesting. Yes. All right. So the next one is the transparent outer coating. All right, go ahead. That's your cornea. Okay, this is the thing that can get scratched. Anybody ever scratched their cornea? Not fun. So yeah. Now the way they test for it is actually really kind of cool. So they will take this dye. It's dye, and it's fluorescent dye. And they'll drip it in your eyes, and then they use what's called a Woods light, which is just a fancy word for a black light. It's a UV light, and they'll shine it on your eyes. And Eunice, where are your shoes? Where are you? Eunice's shoelaces are the exact color. This morning I was like, look at his shoes. Like your eyes will glow this like neon color, right? This like yellow green. And then because your sinuses and your eyes are somewhat connected, when you blow your nose,
It's gonna
you're blowing out like this. It looks like you snorted a highlighter and now you're blowing it out. It's really weird. But they also use wood lights. Like if you have ringworm, which is actually not a worm, it's a fungus, that will phosphoresce. You can see that, like people get them in their hair or whatever, and you hit that with the UV light and it just glows. So interesting, right? They don't have to put chemicals on you for that, like nothing. So you have this sealed fluid-filled capsule that's focusing your light. What's this one? Liam, what's that? That's your lens. You wouldn't think that it's fluid-filled because it appears hard. Like James was talking about popping them out of the fish or the squid or something. Yeah, you can do that. Like when we get into biology year after next, and we do a lot of dissections. Like we do way more than they do in the public school. They get lucky if they get like one thing. We go through like 8 or 9 things. It's great. It was so many dead bodies. Smells not great, but yeah, you can pop the lenses out and actually see them, and they're hard. Like you can bounce them off the table. They're hard. It's weird. Yeah, it's fun. So that's your lens. That's right. All right, and then, go again, go low. All right. So then you have two types of cells. We talked about these last week a little bit. So what is sensing light? Which cells are the light sensing cells? Okay, Lucas. Well, those are rods, and then the cones are color. So you can remember C, cone, color, right? But I want you to look at the cones. What three colors are the cones?
Red, green, and blue.
Red, green, and blue. Why?
Why does blue appear?
Because they're the primary colors of light. What color are the pixels on your TV screen? Red, green, and blue. Did our bodies think that up way before the Yes, we have basically like your advanced screens that we all now use. That's exactly how your eyeballs function. Same way, except sort of in reverse, really. Yeah.
What if it's a color?
So yeah, that has to do, that's more of like a, yeah, it's extra. Yeah, it's more about like having more sensitivity to color. I think it's actually there. I'm not sure. You could look that up and find out. It's not a color. It's more like a separate, and it's like I don't think they're actually like a solid red one and a green one, and they're more like they're bound together. So it's not so much separate, but it is the capacity to like decode that wavelength of light in a way, which is really kind of cool. So now if you've been to the optometrist, you've been through this before, yes. So common vision problems, these are the big ones: nearsightedness, farsightedness, astigmatism. Okay. Who in here has zero correction on your eyeballs? You're just looking at the world naturally and you can actually see it. Some of you are lucky duckies. Okay. So you are emmetropic. You have emmetropia, which means you have perfect vision. Good for you. It doesn't need to be corrected. They call it normal. I'm not going to say normal because most people I know have something corrected. I'm going to call it good vision, perfect vision, non-corrected vision. All right. Nearsightedness. What does that mean, Bailey?
You can't see up close as well. Oh no, it's reverse.
The other way. That's why this one's tricky. Okay. When you hear nearsighted and farsighted, nearsighted is the sight you have. So if you can see up close, you are nearsighted. All right. And then if you can see far but not close, you're farsighted. So it's the opposite of what you're missing. It's what you have. So if you're nearsighted, it's myopic. And sometimes you'll hear this word used in non-medical terms. If somebody has, say, an idea or a plan, or often you'll hear this in political arguments. I'm going to do this, and it's going to save all you people all these problems because I'm a politician and I'm amazing. Sometimes people will say that plan is very myopic. And what that means is short-sighted. Like you're only seeing the immediate result, but not way down the road, which makes perfect sense when you think about what nearsightedness means.
Like, I think it was Ron DeSantis passing that law that every walker had to be like registered and stuff.
Okay.
Which means some of the walkers are gone, which means there's a walk zone.
Yeah, so people were calling it myopic. Yep, so that's exactly the kind of thing. That's exactly the example that people would use. It's myopic. Yep, so you'll hear that a lot. And just in normal language, when you're usually talking about a plan or an idea, or even as somebody's reaction to a situation, like that was pretty myopic. That person didn't think about what was coming. And then farsightedness is hyperopia. And nobody ever says it was hyperopic. I've never heard anyone say that. But I love the jacket. It's really cool. He's slick, right? He's slick. Now notice real quick though, the shapes of these eyeballs. There's your normal vision. That's a pretty nice, fairly round looking eyeball. Your myopic eyeball, look at the lens. See how it's kind of squished? You got a long eyeball. And then your hyperopic, it's a squatty short, it's squished this way. So nearsighted people it's squished this way, farsighted people squished this way. Now lastly, you can also have astigmatism. So this is when you've got this like uneven shape on your lens and everything's blurry and out of focus. And this is really common. And this is, a lot of people don't realize they have astigmatism until they're driving at night. Yeah. Oh, what happens when you drive at night without corrected astigmatism?
Stars.
Yeah, light everywhere, right? Because it's refracting. And all you're seeing is like halos and like beams of light. It's like a light show that you didn't want. Yeah. Yeah.
Stars.
Yeah, they call it halos sometimes, get around everything.
LED headlights.
Oh, I bet.
Oh, yeah, it sucks.
I bet.
I'm trying to figure out if I have that now. 'Cause that's-
No, it's a
Uh-huh.
stars on headlights.
Everything's all flashy and yeah, it's a light show you didn't pay for. So there are ways to correct that. And interestingly, so like Jason is farsighted and has astigmatism, but he has special fancy contacts. Like my contacts just correct my myopia because I'm very nearsighted, but his are special made for him based on the measurements of his lens, and they're weighted because his lenses are uneven as they go. So the lens, if it's a contact, it can't turn. It has to stay exactly right. Like if you're wearing glasses, that lens isn't moving. But if you pop it on your eyeball, it's going to float all around. So it has to stay weighted. So they're weighted and they're specially made for him that corrects the astigmatism. So that's really cool. And they make, sometimes they can do bifocals in contacts. Those are also weighted. If you've ever seen bifocal glasses, now they're smooth, but it used to be like this half moon at the bottom of somebody's lenses that was like really different from the rest, and you could really see it. And it's so when you're looking down, you have better vision up close for right here, and then you can look out and also see. But my dad worked under cars in a pit like this, so he had trifocal, was really bifocal, but he had them special made. So he had like a part down here and up here. He had 2 sections on his glasses so he could look up or down and see well. It was really kind of cool. The only person I ever knew to had them, like the optometrist was like, well, this is a challenge. Let's make the mechanic glasses. So he did. So this is a really good example, shows you how if you're wearing glasses, this is how they're working. And it's really very clear.
Welcome to Moving Math and Science and a demo on how glasses work. As light passes through the lens of your eyes, it focuses on the retina and allows you to see a nice, clear, sharp image. However, sometimes people's lens may be too curved or is too large and the light doesn't focus properly on the retina. Farsightedness, or hyperopia, hyper meaning beyond, means that people can see objects far away, but objects close are blurry because the light is focused beyond the retina. Nearsightedness, or myopia, people can see objects close, but objects far away are blurry because the light is focused in front of the retina. You can go to an eye exam and they'll recommend certain lenses. For farsightedness, it can be fixed with a convex lens, and with a nearsightedness, it can be fixed with a concave lens. Let's find out why. Let's take a look at how farsightedness can be corrected. First, as light passes through the lens, when you're farsighted, you can notice that the focal point here is beyond the retina. So as a result, objects far away will be in focus, but objects nearby will seem blurry. You can correct this by using a lens, and you will use a convex lens. You can see the difference between the 2 lenses here. And here's a little trick how I remember it. The edges of a convex lens are further or far apart compared to the edges of a concave lens. So I'm going to use this convex lens, and you can see when you place it here, it corrects the focal point, and now the focal point is sitting right on the retina, and as a result, objects far away can be seen clearly, and objects nearby can also be seen clearly. Sightedness, you have the opposite. You can see that the light is focused in front of the retina. When you are nearsighted, you can see objects that are near but struggle with objects that are far. You can use a concave lens. Now, when you focus it, you put it on the correct spot, you will notice that now the light is focused right on the retina. Okay, so here it is without the lens, and then here it is focused with the lens. So the near and the middle lens, the concave lens, corrects the nearsightedness. So in summary, a convex lens is used to correct farsightedness, and a concave lens is used to correct nearsightedness. Thanks for watching, and moving that up.
And it's tiny bit. Because like when I look at my contacts, they are so thin. So thin. So does anybody else find this here to be one of the most anxiety producing moments of the year? It's the one that goes like this. Better number 1 or number 2? Number one or number two? Number one, number two. You had this experience where you go to the eye doctor and they're better number one, number two, number one, number two. And you're like, no, please stop. I don't know. They all look the same. Or number two, or number one, or number two. And you're like, ah, and they're flipping the thing. And it's so anxiety producing. You're like, I'm going to fail this test. I didn't even know to study for it. I'm going to fail it. Okay. Here's what they're doing. And I'm grateful for this because I had no idea how this worked.
2, 1, better 1 or 2. 2,
Why is
well,
it-
I'll
Hold up.
1,
Where is that coming from?
2.
Oh, that's not.
Well-
What the hell? That was weird. Oh, look, it's inside. How did that happen? It's like a video in a video. Look at that. Oh, way. I didn't ask you to be there. Or maybe I did. Which one did I want to see? That is really. Ooh.
1,
Well, this is what it looks like, right?
2,
You seen this?
1, 2. Whip.
Yeah, it looks like that. So hang on. Let me take this guy away. Well, hang on. Get big first. Weird.
Better 1 or 2. We've all heard jokes about this phrase and had the anxiety about picking the right one. My name is Jason Foote, and I'm an optometrist at Dixie Eye Care in St. George, Utah. And today I'm going to
Dixie in
demystify
Utah.
this simple yet puzzling question.
Confused.
At the eye doctor, you may remember looking inside of a machine that had a little picture of a hot air balloon or a little house at the end of it.
Seen it?
This is
Yep.
called autorefractor and gives the doctor a starting point for checking the glasses prescription. That starting point is then fine-tuned in a phoropter, which is this machine behind me here. That machine has a lot of different lenses and millions of different combinations. The first step is to make sure the prescription isn't too strong or too weak. The second step is to correct for any astigmatism. Now, astigmatism is irregular curvature on the front of the eye or in the lens. Astigmatism is common enough. Most people have some degree of astigmatism, but verifying the amount and the rotation of the astigmatism is where a lot of those better 1 or 2 questions come in. If a lens is rotated by just 1 or 2 degrees, it's almost impossible to tell the difference between the 2 options, 1 or 2. So that's why bracketing is used. Bracketing allows us to show 2 options that are discernibly different and then move towards the one that's better. And that way, we come towards a final conclusion that's the right lens and the right prescription. For example, if I showed you 2 colors that were right next to each other on a painter's color bridge, you probably couldn't tell the difference between them. But if I showed you 2 colors that were further apart, it'd be easier to tell the difference. Have you ever felt like 1 and 2 look the same?
Yes.
Well,
Every
that's
time.
actually not a bad thing. I feel like as eye doctor, we don't do a good enough job of explaining that that's actually the end point. We want them to look the same because it means that the correct lens is exactly halfway between the 2 bracketed options. The process also has built-in foolproofing, so don't stress next time you go to the eye doctor. Thanks for listening.
Yeah, don't stress. It's necessary because it's stressful. That
I've never been stressed about that.
doesn't stress you out. It'll be like 1 or 2 and I'm like, can I do it again? Can you show it again? Can you show it 4 more times? I don't know. It's too hard. You're going too fast. Like, it stresses me out. It stresses a lot of people out. It's like a running joke. All right. So LASIK. Anybody know anybody who has LASIK? Your dad has LASIK? Yeah? Yeah? Your uncle? Dish? Ah, not surprising. I might do it one day. I'm afraid to do it too early because I know I'll be freaked out by the whole thing and you have to have it like revised every so often. So I'm kind of waiting so I don't have to have it revised too much. Because I don't want to do it too many times. Because you're awake, right? So this is how it works. Like the whole concept. How does laser eye surgery work?
In 1948, Spanish ophthalmologist Jose Ignacio Baraquer Monet was fed up with glasses. He wanted a solution for blurry vision that fixed the eye itself without relying on external aids. But the surgery he eventually devised was not for the faint of heart. Baraquer began by slicing off the front of a patient's cornea and dunking it in liquid nitrogen.
Nice.
Using a miniature lathe, He ground the frozen cornea into the precise shape necessary to focus the patient's vision. Then he thawed the disc and sewed it back on. Barachel called this procedure keratomylusis, from the Greek words for carving and cornea. And though it might sound grisly, his technique produced reliable results. So, how did Barachel's surgery work? Keratomylusis corrects what are called refractive errors, imperfections in the way the eye focuses incoming light. Ideally, the cornea and lens work together to focus light on the surface of the retina, but several kinds of refractive errors can impair this delicate system. In people with myopia or short-sightedness, a steep cornea focuses light just short of the retina. Those with hyperopia or farsightedness have the opposite problem. Light is focused too far beyond the retina. And in people with astigmatism, the cornea has two different curvatures, which focus light at two distances and produce blurry vision. Even those with perfect vision will eventually suffer from presbyopia, or aging eyes. As the proteins in the lens age, they slowly increase its size. By an adult's mid-40s, the lens is too large to easily change shape and shift focus. Glasses and contact lenses bend light to compensate for these refractive errors. But as Barachel's procedure shows, we can also alter the shape of the cornea itself, moving the focal point backwards, forwards, or pulling a divided image together. And thankfully, modern eye surgeons can sculpt the cornea with far less invasive tools. In corrective laser eye surgery, surgeons rely on excimer lasers. These tools are accurate enough to etch words into a human hair. To safely accomplish these ultrafine incisions, they use a technique called photoablation. This allows the lasers to essentially evaporate organic tissue without overheating surrounding eye tissue. So how does laser eye surgery actually work? The first step is to separate a thin layer from the front of the cornea. This can be done with either a flat, wide blade or a femtosecond laser that produces millions of tiny plasma bubbles to create a plane beneath the corneal surface. Surgeons then lift the flap to expose the inside of the cornea. Guided by the refractive error and the shape of the cornea, the excimer laser robotically sculpts the exposed corneal bed into the correct shape. This process usually takes less than 30 seconds for each eye. Finally, the flap is closed, and its edges reseal themselves in just a few hours. Because the lasering is done on the eyeball itself, it's described as in situ or on site. Its complete name is laser in situ keratomylusis, but you probably know it as LASIK. Essentially, this technique carves a patient's contact lens prescription onto their cornea. Like any surgical procedure, LASIK comes with certain risks. Some patients experience slightly blurred vision that can't be corrected by glasses, but the technique is currently about as likely to damage your eyes as wearing daily disposable contact lenses for 1 year. Today, a technique called SMILE enables surgeons to sculpt the cornea through even smaller incisions, further reducing recovery time. And lasers aren't just correcting the 3 types of refractive errors. This technology can also restore aging eyes. In a technique called laser blended vision, surgeons adjust one eye to be slightly better at distance vision and the other to be better at close range vision. The difference between the 2 eyes is small enough that most patients can merge their vision, allowing both eyes to work together at all distances. Advances in laser technology continue to make vision correction surgery more effective and accessible. One day soon, Barachel's vision of a world without glasses may finally come true. Did you know that you're crying right now? Our eyes are constantly producing tears.
You're crying. So really weird, right? So like,
How expensive is that surgery?
you know, it's usually covered to some degree by insurance. It used to be like very, very expensive. I'm not, hey, Alexa, how much is LASIK surgery on average?
According to an Alexa Answers contributor, while charges for LASIK procedures vary widely by practice and region, the average cost of LASIK is between $1,500 to $3,000 per eye, depending on the type of the procedure, surgeon, and region of the country.
That's really not too bad if you think about it. Yes, so wait a minute, don't get up. Wait, I didn't say you're done yet. Wait. So other things that happen as your eyes age, this is a terrible word for it, but you can get what are called floaters. It's not what it sounds like. Yeah, basically over time, your retina degenerates a little bit and like bits of that tissue kind of sloughs off. It's okay. Kind of sloughs off and it floats around in the aqueous humor. And occasionally we'll be looking at a light source and this thing kind of floats through. It's like this blurry blob. Do you know somebody who has it?
My mom had it.
Have it too?
It happened at night out in the woods.
Oh, no.
That for a couple days.
Here, shut the door. Yeah, so Jason got him first and they freaked him out. And then so I knew about it, so I knew not to be freaked out by it. But it's a weird thing. They're not even like, it's not like solid things. And you get to the point where you don't see them anymore because it becomes it's like seeing your nose. You don't see it anymore. But sometimes you'll notice them and you'll be like, oh, there goes like a little, woo, what was that? Right? That's weird. And they can do that blended vision with contacts and glasses too. So like I tried it with contacts for a while where the one was supposed to be better for close up and one was better for further away. And it was really weird. Does anybody have the issue where like you wear contacts usually and then you put glasses on and the world is weird? Like real weird? Like who's myopic? Who's nearsighted? I'm nearsighted. Anybody know your prescription? Like, you know yours?
6.5.
Minus 6.5? You is blind. Like real blind. I've got minus 4.75, minus 5.25. So the negatives are the nearsighted people and the positives are the farsighted people. So
That's better than what I used to have. I had limited computer time, no games, no stuff.
yeah.
For that, I used to game for like 3 entire Saturdays and days, and I went up to like 8 and 9.
Yeah. So if I wear my glasses, which I very rarely do, in order to focus things, they are shrunk. Like they're literally smaller than they are in my peripheral vision. So I have to walk down the stairs like this. Because if I'm looking straight ahead, this is smaller than this and I will fall. Like, and I also the weird thing is I put too much food on my plate because I'm like, it's not enough. And then I can't eat it. And I'm like, why am I not? Because I put enough food on there for 3 people because it was small because I can't see it. Right. So vision's weird, but we can do all kinds of cool stuff with it. And like I mentioned last week, if you have cataract surgery, when they replace your lens with a new lens, it's a corrective lens. So it's like an installed contact. It's like an embedded contact. Now, do you know what glaucoma is? Do you know what that is?
Oh, I recognize the one.
Yeah. When you go to the doctor, they do that puff of air or they touch the thing on your eye. So it's pressure in your eye. There's obviously fluid in your eye and it needs to move from one part of your eye to another part of your eye and it can build up too much. Do you know how they fix that? They actually drill a laser hole in your eye. This one up here had it done and he came home and he's like, can you see it? And I'm looking, I'm trying to find a little hole because they make a little hole in your eye. And then you have to go back like every year and they check and see if the hole's still there. But it's almost like a whip. It's like, and it's done. You don't feel it, but they drill a tiny hole in your eyeball to let the pressure, so that the pressure can equalize. It's really kind of cool. So,
but nothing I've ever went.
yeah. I don't like the puff thing. Does anybody else jump out of a chair when they do that puff of I know it's coming. I know it's coming. I can't help it. And I've seen the ones where they actually touch your eye with this little thing.
No.
I don't like that one much, but so yeah.
I'm not sure if you were told that it was gonna touch your eyes, but I would just put them to a machine. I'm like, oh look, a little house, and then
Get off my face.
I just said like, I'm one of those people that always jumps.
Uh-huh.
I always have to do it like 3 times because I don't remember like my lens is unusually thick or something like that.
Oh,
So we'll
interesting.
do the pop, like I jump, like let's do it again.
No, but that's torture. That is like, that's anti-Geneva Convention style torture. Like, that's not cool. Yeah. Well, also like everybody's retina looks different. Like somebody told me once mine was sparkly. I'm like, what does that mean? They're like, yours is shimmery. Not everybody's is shimmery. And she's like, you know, like really looking at it. So I'm like, just please tell me that I don't have any macular degeneration issues. That's what I'm careful about. Really careful of that because I don't want to do. It was the weirdest thing. He woke up one day and that was it. He was just blind for the rest of his life. He was well into his 70s when it happened, but it was weird. You go to bed and you wake up and you can't see. And I'll never forget that. You ever seen with like the oil and water, the little containers with the oil and water? That was what it was like in his eye, like this is gross. It's like,
You
but
get surgery to fix that?
they can like drain some of it out, but the damage is done. Nowadays they can fix it a little bit. Back in the 90s when it hit him, there really wasn't much you could do about it. But that man still got in his car and drove the 4 blocks from his house to the oceanfront on a regular basis because he said, I've been doing it for years. I know where every curve is. We're like, hey, what if a dog goes out in front of you? Like you can't see in front of your face. So my mom started pulling the spark plugs out of his car. And he couldn't see them well enough. So then he'd complain and call my dad, and my dad would go and fix the car. It was a thing. It went on for years. He also continued to use chainsaws and all kinds of things because old men are stubborn. Yeah, it really is really weird. Okay, so on your way out, a couple things. There's Valentine's lollipops. Take you one. When you're getting your candy from the candy machine, there are little tiny paper cups that I put over here. Please use those and not the bigger ones out of the cabinet. Because if you're pulling them out of the chest, those are the ones that we're supposed to have for like when we have a party, you know? And if you're walking out the door with the big paper cups every day with like 7 jelly beans in it, so you're going to be sticking your head under the faucet at a party because there's not going to you're going to have no way to drink anything, right? And then next week is winter break. So we're not here, right? So you're going to take a nice break and enjoy yourselves. Questions about today? Are we good? Excellent. All right. I'll turn this around so y'all people can get to this. Yep. Oh, Drew's there. Hang on. We'll do it like so. What are we looking up?
Mewing.
Mewing?
Yeah.
Like a hawk?
It's good for your jawline.
What is it?
It's mewing, like you have your tongue to the roof of your mouth.
Uh-huh.
It makes your jawline more defined or something.
People say it's good.
Yeah.
I figure I've got tech neck and I'm just screwed, you know, it's just the way it's gonna be. I don't even try.
I took them.
You took, oh, where are yours? Do you have yours?
Yeah, I took them.
Oh, okay, all right.
Like what are Valentine's lollipops?
They're by the door. They're in
Like
the,
what are they made of?
they're just like strawberry. I can look them up. Do you need to know all the?
Are they like, no, I just don't usually like lollipops, so it's like chocolate or something.
No, they're not chocolate. They're like
Is it
strawberries and
white
cream
or-
flavor or something.
Is it white, like the same texture?
They're just like hard candy, like lollipop. They're not chewy. or-
This chair. I don't usually.
Isn't that fun?
I
You have
don't-
to step on the back of it and pull up. It's like a puzzle.
I just.
There you go. Isn't that weird? They don't.
I usually like lollipops, so I was just wondering.
Okay, well, you can take one and if you don't like it, you can throw it away. Not a big deal, one way or the other. You feel okay? You better? Does your head hurt? No, you look like you're like back there. I'm making clear.
Tired.
Yeah, I get tired. Excellent.
My dad's cool, but it was like.
Ooh.
I don't remember what it's called, but like his eyes like smush, which makes it. It is.
Real bad. Yeah. That's rough. That's really rough.
So it's not like
Mine are like-
your second or first night. I know that is like you said, odd things.
That's crazy.
I think,
What were you saying?
I think my eyes are on like 5.
Yeah.
I'll let you go.
Mm-hmm. That's me.
Oh, my
I'm
eyes
right.
are, but
Yeah.
when she got new glasses,
Mm.
she had to get new glasses because her glasses weren't working anymore.
Yeah.
And because her contacts were messing with her eyes,
Mm-hmm.
but they had to file them down a lot, because she is.
Yeah.
I don't know what her prescription is, but like on the side of her glasses, because she got like the kind of like top.
Oh, yeah. Are you saying that past the frame?
It's like the
Yeah.
back is like this thick. on
I've
the
had
side,
ones like that. They're like, these really aren't gonna fit in your frame. I'm like, look, I'm gonna wear them only when I can't wear contacts, so it's fine. Just deal with it.
It's crazy.
It's weird. But when I put mine on, I'm literally like, oh no, I'm walking downstairs. I can't do that. I can't see. It's crazy.
She also doesn't like living
at night because she gets night blindness. And
Yeah.
she has astigmatism.
Yeah, that's uncomfortable. Like, it's hard to see and it's, you don't wanna be like that. Nobody wants to be like that.
I was thinking, I was like, do I have this face? Like my brother has it,
Mhm.
my mom has it, I think my dad. might
Very
have
common.
it.
Most people have some degree, you know?
But for this, like, cause I see like, they're not like circles, but they're not like, you know, the pictures of the stigmas.
Yeah.
It's like this.
Yeah,
It's just like that.
little bits. Yeah, probably some degree. Yeah. When my grandmother had her cataract surgery, we only ended up doing one eye because it actually, there was some major problem with the surgery and it like, basically her eyeball died. Like it kind of shriveled up and got cloudy and gross, like it didn't work after that. I don't know what happened in that surgery, but then she became completely blind in that eye and the other eye was all cloudy and we were like, you're not doing the other eye, that's not gonna happen. So she was also mostly deaf, so she had a lot of sensory deprivation at the end of her life, which didn't help when the dementia kicked in, she couldn't see or hear, it was like, oh, this is fun, not the way to be. But my grandfather literally just woke up one morning and he's calling people, he's like, you have to come help me, I can't see, something happened. And we get over there and we're looking at him, like, pulling up to the window where the daylight is, like, come here in the light, and this whole, you could just see it, it was so weird. Grody.
My dad said I don't think he said he was born with it. I think it's because he rubbed his eye so much when he was
Oh,
little.
really? Did something to it?
I don't know. I don't entirely believe it because, but also
Dad stories. Yeah.
me or my brother don't have it.
Yeah.
And
Well, that's it. You don't want it, I'm sure.
No,
Mm-mm.
but he had to get surgery on his eyes. I don't know what happened, what he did, but I can remember him having like a thing on his eye for a while.
Oh, yeah. Well, my mom had her cataract surgery. So her lenses, they're called toric lenses, but they're the kind that are adjusted for astigmatism. And they have like little hooks on them. So when they put them in her eye, they like put them in with the hooks in such a way that they don't move at all. So if she has a lens on the cornea that's like, it's hooked, so it's not barbed, right? And it corrects the astigmatism in her eye. And she was super excited the first time she saw with the patch off because she could see individual leaves on a tree. And the patch was just like a blob of a tree. And she could see, oh, because her vision was like corrected. She needs readers, but she can do without, she can do that.
I remember my dad's not wearing his
Pretty
contacts,
cool.
like when he's in bed. He looks at his phone like this. like,
Oh, yeah.
in his face, I think because he can't see it.
Bye.
But also it's only ever one eye, so like the other eye's closed and he's just